Okay, here we are with the final exam review for MAC1105, and we'll work through these problems and see where we get. The first problem asks us to find the distance between these 2 points, and the points given above are 4, -5, and 3, 2. And if you remember the distance formula, this we'll call x1, y1. And this we'll call x sub 2, y sub 2. And the distance formula is the square root of the difference in x's squared plus the difference in y's squared. And the difference can be taken in either order. Squaring doesn't make a difference in the end. So we have then 4 minus 3 squared plus -5 minus 2 squared, which becomes 1 squared plus -7 squared. 1 plus 49 square root of 50. And you might notice the square root of 50 isn't there. You could check with your calculator. But if you realize the square root of 50 is the same as the square root of 25 times the square root of 2, then that's the same as 5 square roots of 2, which would be B. Okay. The next problem asks us to find the midpoint of the same line segment. And the midpoint formula is just the average of the x-coordinates. That is, it's halfway between the x's and it's halfway between the y's. It's a point. And so in our case, we're going to get 4 plus 3 over 2 and -5 plus 2 over 2. And out of that we get 7 halves and -3 halves. So the correct answer here is C. Now we're asked to find the center of the circle whose equation is given. And the standard form for a circle is x minus h squared plus y minus k squared equals r squared, and the center is at hk, and the radius is r. So we see in this case, the center is at 3, and this, remember, is y minus -4. 3, -4, and the radius equals 7. So the correct answer is A. In number 4, we're given this equation, which is not in standard form. And so to do this, we're going to complete the square. And this is not a big deal, but this is one of the reasons why completing the square might be useful sometime. So I'm setting it up with x squared minus 2x plus something, plus y squared plus ay plus something equals a plus something plus something. I've moved the a to the other side. We want to complete the square in each of these cases. Half of -2, and this depends upon the leading coefficient being 1. Half of -2 is -1, squared is 1, so we add 1 to both sides. Half of 8y, half of 8 is 4. 4 squared is 16, so we're going to add 16 to both sides. And out of this we get that x minus 1 squared plus y plus 4 squared equals 8 plus 1 is 9 plus 16 is 25. The center would be at 1, -4, and the radius would be 5. Center is at 1, -4, and the radius is 5. Now number 5, we're looking for here the set of all x such that this expression is real And for that, we need x squared minus 4x to not be 0. So what I'm going to do is I'm going to find out when it is 0. And then I'm going to say I don't want those two. Namely, I don't want 0 or 4. Namely, in this case, you can see the answer would be A. Okay. Adjust this a little bit here. Okay. All right, number 6 asks us another domain question. In this case, f of x is the square root of x plus 2, and for this, we want x plus 2 to be greater than or equal to 0. And that says that x would be greater than or equal to negative 2. And remember, or equal to, we are allowed to take the square root of 0. So greater than or equal to negative 2 would be C. The slope of this line is negative 5/3, and that tells us the slope of a perpendicular line would be the negative reciprocal, or opposite and reciprocal, which is positive 3/5. The answer would be A. The slope of the line through these points, and again, these points are labeled x1, y1, and x sub 2, y sub 2, and the formula for slope, difference in y values divided by difference in x values. In our case, the slope will be the difference in y values, 4 minus negative 2 over 7 minus 3, which is 6/4, or 3/2. The correct answer would be D. Now, number 9, we're trying to determine if this graph is symmetric with respect to the x, the y, or the origin. We see if we reflect it across the y-axis, the graph is unchanged, so it does have y-axis symmetry. If we reflect across the x-axis, the graph is also unchanged. And if you remember that origin symmetry is the succession of a reflection across the y followed by a reflection across the x, or at least it's equivalent to that in this flat space, then we get that one for free. So it has symmetric with respect to x-axis, y-axis, and origin. Now there's 2 ways to do number 10. You can do it with algebra. That is, you can check. For y-axis symmetry, we would replace x with minus x. And if the equation is unchanged, then we have symmetry. For x-axis symmetry, we would replace y with minus y. For origin symmetry, we would do both. And we can check to see that if this equation, and thus its solution set, is unchanged under those replacements, then it would have the symmetry. If we replace x with its opposite, we can see the absolute value will contain that, and we will have y-axis symmetry. If we replace y by its opposite, it's doubtful, you can check, that this will be the same equation. It'll be a different equation and have a different graph. And if we do both of those, we'll get a different graph. So it should only have y-axis symmetry. And an alternate way of doing this is to take your calculator, and let's go ahead and put this in. Write it as y equals the 2 absolute x plus 3. And I'm going to go ahead and type that in my calculator. Math, numeric, 2 absolute x plus 3. And you can see, at least this graph does seem to show y-axis symmetry. And it doesn't have x-axis symmetry. If you were to reflect across the x-axis, we don't see a matching graph down here. And origin symmetry, if you do both of those or equivalently rotate 180 degrees, we also don't see that symmetry. So number 11 we want to reflect across the y-axis, and to do this, if you remember, take a point here. To reflect it across the y-axis, which is to take it over here, the coordinates will be minus x comma y. So we need to replace x with minus x. If we start with this, and we want to reflect it across the y-axis, we should replace x with its opposite. So the answer would be B. In this case, we're going to replace x by x plus 3. Will shift us to the left 3 units. And we can see the answer here would be B. And if you wanted to verify this, and this is kind of slow, but remember you can do any of these by hand. We could look at the graph. Let's see if I can fit this in here. Yeah, we can fit these in. If we looked at the graph of square root of x, there's the graph of the square root of x function. We could zoom in a little bit. And we wanted to check one of each of these. Well, we could check that the square root of x plus 3 has been shifted to the left by 3 units. And there you can see it's shifted to the left by 3 units. Shifted down 3 units, and this we're going to replace y by y minus 3. In this case, we're going to replace y equals f of x with either y minus y plus 3 equals f of x, or y equals f of x minus 3, depending on whether you like to see it as a functional form or not. And again, you can verify this experimentally. You can type each of these in and verify that D will be shifted down by 3 units. Number 14, we want to shift 1 unit to the right and up 2 units. Right. So we're going to start with this, and we're going to get y equals, this first case, we'll get y equals f of x minus 1, and we want to shift that up 2 units. We can either then go to y minus 2 equals f of x minus 1, or y equals f of x minus 1 plus 2. And that would be our square root of x minus 1 plus 2. And that would be D. And you can verify again that D is the correct answer. Now, number 15, stretched by a factor of 3. This is one of those ones where, first of all, you don't have to worry about it, but vertically stretched. If you stretch vertically by a factor of 3, the answer would be D. If you stretch horizontally by a factor of 3, the answer was C. And this is just poorly worded. Don't worry, you won't get any of these questions on your final exam. Okay, number 16, we want to reflect across the x-axis. And reflecting across the x-axis, this is replace y with minus y and shift down 4 units. All right, so we're going to start with y equals f of x, or y equals the square root of x. And then we're going to go from there, we're going to go to y equals minus the square root of x. And then we want to shift that down 4 units. And for this, we can replace y by y minus 4, or y plus 4 actually, or we can simply subtract 4 units from the previous y value. And so we get minus root of x minus 4. And let's check each of these in turn. And the correct answer for this would be minus root of x minus 4. There we go. A. Let's check that this does match. Minus root x minus 4. So what we're looking for is something that's been reflected across the x-axis, and then it's been shifted down by 4 units. Here's our original square root, And there we have reflected across the x-axis. So if we were to take a point, so there's the point 4, 2. If we reflected across the x-axis, then we would go from 4, 2 to 4, -2. And then if we shifted down, we should be at 4, -6. So that's the right graph there. Now the next one, we have a piecewise function. And this is giving us 3 pieces. And when x is 4, we're going to be using this formula. So f of x equals x when x equals 4, so f of 4 equals 4. F of x in this case, when x is -1, equals 3x plus 5 when x equals -1. And that tells us that f of -1 would be 3 times -1 plus 5, which is a +2. In 19 to 21, we want to match these equations. For example, here's f of x, and I can barely see where the axes are. Maybe if I have a pen, I might be able to darken in these axes. Graphics will be much better on the final exam. There is the x-axis, and there is the y-axis. Okay, and here we are. Here's the x-axis, the y-axis, and here is the x-axis in each case. So we can see where it is relative to these. Yes, it's almost like an M.C. Escher drawing here, trying to figure out where things are. So, in the first problem, we're given f of x, and we'd like to find out what is f of x plus 2. This one has been shifted left by 2 units. So if we look at these, I'm pretty sure that A is the one that's the graph of f that's been shifted left. And in the second one here, we're going to shift down 2 units. And the only one that seems to be shifted down 2 units would be D. And in this case, we have 2 things going on. This guy is going to reflect across the x-axis. And this guy is going to shift left 1 unit. So we want to reflect across the x-axis. That'll make this shape seem to be a V shape. And then we're going to shift left. And by default, it must be B. So I'm not even going to look at the scale. All right, for number 22, we want to graph this function, find the axis of symmetry. And we know the axis of symmetry is a vertical line. I'll just draw a generic. Right. It's minus b over 2a, f of minus b over 2a. And the axis of symmetry is this guy, whose equation is x equals minus b over 2a. So all we need to do is find the a and the b and the c in this case. In this case, 3x squared minus 5x plus 4 is standard form. And so x equals minus b over 2a, in this case, is minus 5 over 2 times 3, which is 5 over 6. And we get positive 5 over 6, which is b. The next one, it is in standard form, and we have minus b over 2a again, so is the x-coordinate, and the y-coordinate is, of course, f of that. And the x-coordinate in this case is minus 120 over 2 times 30. And let's see what that is equal to. That's 120 over 60, that's 2. And f of 2 in this case, well, let's see, we might be able to do it by hand. That's 120 minus 240 is negative 120 plus 148. I believe that's 28. Okay. And again, this is something you could verify experimentally by drawing it on your calculator. Let's go ahead and do that. 30x squared minus 120x plus 148. Let's go zoom 6, and I'll go out a little bit. I don't see anything. Zoom 3, enter. Barely seeing it. Wow, this is a good one then, because we can't see any of the graph. In trace mode, I can see I'm at 0, 148. At 2, I am at 28. And if we were to go second trace minimum, and let's see, make the left bound -1 and the right bound 5. And it says that the minimum is pretty surely at 2, 28. So that was a little hard to see without a good window. Okay, here's another function. It's a quadratic function. Again, in standard form, it would be minus 3x squared plus 12x plus 11. And we want to know if it has a maximum or minimum and what that value would be. Well, it's a parabola because it's quadratic. It opens down because the leading coefficient is negative. And because it opens down, it's going to have a maximum. And that maximum will be the y value of the vertex. If it opened up, the minimum would be at the vertex and it would be the y value. So in this case, we know that it has a maximum, so it's going to be either C or D, and we just need to find minus b over 2a. And my guess is they're going to try to fool us with a few things, but let's go ahead and look at this. Minus b is minus 12 over 2a, 2 times negative 3, and we get negative 12 over negative 6 is positive 2. Well, they're not trying to fool us by telling us that the maximum value is 2, but let's go ahead and check it what the value of the function is at 2. Negative 3 times 4 is negative 12, plus 24 is 12, plus 11 is 23, so the correct answer is D. I don't know where the negative 1 would have come from, and if you were to graph this, it should be fairly obvious that you're getting that value. Number 25, we have 2x minus 9 is 3, and one of our transformations says that this will give us 2x plus 9 equals 3, or 2x minus 9 equals negative 3. And each of those can be solved by adding 9 and dividing by 2. So x is 12 over 2 is 6, x is 6 over 2, or 3. And so we get the solution is C. In number 26, we get, in this case, if you go 7x minus 3 equals 0, or 7x minus 3 equals the opposite of 0, you get the same equation twice. In either case, if you add 3 and divide by 7, you get x equals 3 sevenths. So there is only one solution in this case. That is 3 sevenths. These can all be done on a calculator. Number 27, to transform this, to do it algebraically, we get absolute 7x minus 2 equals 9, and we're stopped because the absolute value can't equal a negative. Now, if you were to go and attempt to solve this algebraically, you'd be making a false assumption that you can transform that. And here's a good example of seeing how the solution shows up on a calculator. So if we were to type in, we can do it either way. I'm going to go ahead and type in absolute 7x minus 2 plus 9. All right, there we go, zoom 6. I don't know if you saw just a little bit up there. We can zoom out maybe. There we go. We can see this graph. When does this graph equal 0? Well, it never equals 0. Okay? And so therefore the solution is the empty set, or there is no solution. D. In number 28, the discriminant, remember, the solutions via the quadratic formula are minus b plus or minus square root b squared minus 4ac all over 2a, and the discriminant is that thing. If that's 0, which of the following describes the solutions of the equation? Well, assuming all the a's and b's and c's are real, that we have real coefficients, we're talking about a parabola, and the solutions are at minus b plus 0 over 2a and minus b minus 0 over 2a. And if you add 0 to a number and then subtract 0, you get the same value. So we actually have the same solution twice. This is equivalent to a parabola whose vertex lies on the x-axis. And we have one real solution repeating. And again, assuming that the coefficients are real. Okay, this next one. 2x plus 3 is less than 7, and 2x plus 3 is greater than negative 7. And you can write this as a triple, unlike the other transformations. And however you want to solve it, I'm going to go ahead and solve this triple. Minus 10 less than 2x less than 4, minus 5 less than x less than 2 is our solution in terms of an inequality. And minus 5 to 2, the interval would be our solution. Number 30, convert the equation a to the b equals x into a logarithmic equation. Log base a of x equals b. And right off the bat, it's a. There's two ways of doing this one, not 3 or 4 ways, including your calculator, including checking by inspection. And I don't know, truthfully, I could check and see that 0 doesn't work because 0 would make the left-hand side 25, so that doesn't work. And then plugging these numbers in, I'd probably do that in the calculator. Well, I don't know. It depends on how you want to do it. I think the solution is C, by inspection. But let's go ahead and do it. One way is to be slick and to notice that the left-hand side can be written as a power of 2, and the right-hand side, a power of 5, and the right-hand side can be written as a power of 5. And so then we can simply equate, because these two have the same bases. So negative 4. Solution to bx is negative 4/3. Another way to do it, in the interest of doing it as many ways as possible, take log of both sides. Now you could take natural log, you could take base 10 log, you could take base 5 log, which I think would be a little bit, and I'll just call this ABC. You could take log, it'll be a little bit easier to take log base 5. And I'm not going to simplify, that's just a number. In any case, I get x is equal to log base 5 of 1/25 minus 2 over 3. And I can check that on my calculator. Log base 5, and I need to do this with the change of base formula. There's my numerator. Log of 1/25 divided by log of 5. There's the log base 5 of 1/25 minus 2, close my numerator, divide by 3. And that actually is a fraction. If you remember, pressing math, enter, enter, gives you negative 4/3. Okay, so C is our answer. And similarly, 32 has the slick way and the non-slick way. The slick way is to recognize that these can be written both as the same power, 2 to the 5th to the x plus 2, and 2 squared to the x minus 1, which would be 2 to the 5x plus 10 equals 2 to the 2x minus 2, so that we have 5x plus 10 must equal 2x minus 2. And if we subtract 2x and subtract 10 from both sides, we get 3x equals negative 12, so x equals negative 4. See, you could, of course, plug these numbers in one by one to see which one worked. You could also take logs of both sides. Now, taking logs of both sides, let me get a piece of paper and I'll show you. It's a little bit messier than you might think, but it does work out. So if we started with 32 to the x plus 2 equals 4 to the x minus 1, it's a bit of a drag, but let's at least pick, well, let's just go ahead and take ln. So ln, which is fine, gives us a little bit more writing. So we get the natural log of the left-hand side equals the natural log of the right-hand side. Now, one of our properties of logarithms is that we can bring these exponents out front. And remember, natural log of 32 and the natural log of 4 are just numbers. And this is a linear equation in x, so x natural log 32 plus 2 natural log 32 equals x natural log 4 minus natural log 4. The terms involving an x need to be together, so I can subtract x ln 4 from both sides. And the terms that don't involve an x can go to the other side, so minus ln 4 minus 2 ln 32. And to combine these terms, we can factor out what makes them like. That was an ln 32 there. That would help to transcribe your things correctly. And so dividing both sides by the coefficient of x, we get minus ln 4 minus 2 ln 32 over ln 32 minus ln 4. And if we were to do that in our calculator, let's just go ahead and verify that we get whatever pretty number we were hoping to get at the end. And so we get, parentheses, minus ln 4, close, minus 2 times ln 32, close that, close our numerator, divided by, open our denominator, ln 32, close, minus ln 4, close our denominator, and we get negative 4 in the end still. Okay. Describe how you would get the graph of this from the graph of this. Well, first thing we might do is replace the old y values with the opposite of them. And this is a reflection across the x-axis. And then we might go and subtract 3 from this. That would be shift down 3. Now let's see if just looking at it straight up gives us any other possibilities. Let's just see. So minus 2x, 2 to the x minus 3. Okay. Let's see what we get. So we start with 2 to the x, which looks like this pretty basic exponential graph coming up. Whoops, hold on, let me check my window. Aha, 2 to the 9x. It's not bad. It's 2 to the x. A little bit better, basic exponential graph. And we're going to come up with a new graph called minus 2 to the x minus 3. Now we're claiming that it's been first reflected across the x-axis and then shifted down. So what was the horizontal asymptote of the x-axis has now been shifted down and the graph's been reflected. And if you do these two operations in the opposite order, if you first shift down and then reflect, you'll get a different graph. So do be careful that these two operations aren't commutative. You can't do them in either order and get the same result. In fact, if you wanted to, let me see if I can fit it in down here. If you wanted to start with f of x equals 2 to the x, and first do a shift, you might look at this, you say, well, how can I do a shift first and then a reflection? You would have to shift it up by 3 units. If you look at the second graph, what was at 0, 1 is now at 0, negative 4. So you need to shift this up by 3 units first and then reflect across the x-axis. So we would have then shift up by 3, then reflect across the x-axis. But in all our cases, our answers first begin with a reflection, so at least that part's easy. Reflect across the x-axis and then shift down by 3 units. So B, C. All right, log base 5 of 13. No easy way to do this other than change a base formula. So we could do log of 13 divided by log of 5. Or we could do natural log of 13, divided by natural log of 5. 1.593, etc. To the 3 decimal places, the nearest thousandth would be 1.594 in either case. Which of the following is a one-to-one function? Hopefully all these are functions. You could graph them and see which ones pass the horizontal line test. Let's see if any of these have a case where two different x's go to the same y. So, for example, I'm looking at these y values, looking for a match. Here are 2 y values the same, and 2 different x values go to this one. So this one's not one-to-one, whether it's a function or not. And again, let's see. This one looks like good. We don't know if it's a function or not. Here again, it's 2-to-1 with these 2. And here we don't see any matching, so this is a candidate. But then if you look more closely at this one, you'll see that the same x value is not a function. The same x value goes to 2 different y values. The correct answer here would be B. And if you were to graph this is kind of silly, but graphing each of these, you would look for something that passed both the horizontal and the vertical line test. So if we were looking at -3, -9, I'll make that my scale, -3, -9. There's 1 point. I'm going to graph B. -1, -1, -1, -1 would be, say, about right there. And 1, 1 would be about right here. And 3, 9 would be about here. You can see here is a graph, and it's not connecting the dots. It's just those 4 points. Passes both the horizontal line test and the vertical line test. So it's a function because it passes the vertical line, and it's one-to-one because it passes the horizontal. Which of the following is not a one-to-one function? Well, these are all written as y equals some expression of x. These are all functions first. And if we think about them very quickly, we can come up with this is not, because it's a parabola. So it fails the horizontal line test. Number 37, which of the following is the inverse of this? And again, the easiest thing is probably just to find the inverse. The inverse looks like 3y plus 1, and to solve for y, x minus 1 over 3. And so f inverse of x should be x minus 1 over 3. And we see D is the correct answer. And these 2 questions were given function f, which is a line, and g, which is a parabola. We're asked to find g composed with f of 2, and we know if you read it as g of f of -2. And f of -2, you can see, would be 5 times -2 plus 2. So that would be -10 plus 2, or -8. So this would be g of -8. And g of -8 would be -8 squared minus 3, which is 64 minus 3, or 61. So the answer here would be D. F of g of 2a. First thing is write down f of g of 2a. And now g says we're going to take our input and square it, and then subtract 3. So we're left with f of 4a squared minus 3. And f is going to take our input, multiply by 5, and then add 2. So we have 5 times our input plus 2. So we get 20a squared minus 15 plus 2, or 20a squared minus 13. So B would be our answer. Next one. Same function before. We'll have to look at this. I'll bring it back. G was x squared minus 3. So g of x was x squared minus 3. So we're asked to find g of a minus 2, and we know that's a minus 2 squared minus 3, and you can see the answers here have been simplified, so we'll go ahead and simplify this. Foiling this out, you get a squared minus 4a plus 4 minus 3, and don't forget, please, don't make the mistake of doing this incorrectly. And then you get a squared minus 4a plus 1, which is a. Which of the following is an equivalent expression to log base b of 3x squared? Log base b of 3x squared, well, we can split across the multiplication. Log base b of 3 plus log base b of x squared, and then the exponent can come out front of this. So we would get then log base b of 3 plus 2 log base b of x. Log base b of 3 plus 2 log base b of x. Which of the following is equivalent expression to this? And again, we split across this. Log base a of 2m minus log base a of n. And the first one can split just a little bit further. Log base a of 2 plus log base a of m minus log base a of n, if I can fit that in. So let's see which one of these. Here we go, D. Number 43, which of these most closely resembles the graph of log base 3 of x? Well, the easiest thing here is let me just graph log base 3 of x. Show you what it looks like. Log of x divided by log of 3, change a base there, and you can use ln if you want, zoom 6. That is what a basic logarithm looks like. So I would say it has to be C by default. All right, number 44. Convert the following. Log base m of n equals x into an exponential equation. Remember, the base is the same, so it's m to the x equals n. And the answer is D. This first one, part 2, free response. Show your work, such as a graph used to think about your answer, etc. In this case, we're solving for C. We can see it in the denominator. We're going to multiply both sides by the LCD, the only D. So we get 6ac plus 2a equals 5b minus c. The terms involving c are here and here. To bring those together, we're going to add c to both sides and subtract 2a. And combine the terms involving c. Remember, c is what we're looking for. And we get c is 5b minus 2a over 6a plus 1. The next one, we're looking to solve this cubic equation. A little extra paper here. We have 6x cubed plus x squared equals 12x. And again, you can do this in your calculator, but you need to show your work, so we're going to do it by hand. Standard form. Factor out of GCF. Now this is a tough one to factor. I'm pretty sure it factors, but remember I still have the quadratic formula. I'm going to give myself a little bit of time. And I'm going with either 6x and x, and I think I'm going to go with 3x and 2x. Now that could be a 4 and a 3. I'm going to go with the 4 there and the 3 there. And I'm going to go with plus there and a minus there. Let's see if that works. 6x squared minus 12, wouldn't have put them down if I didn't, minus 8x plus 9x plus x, that works. Okay, and again, quadratic formula is still available. So I get 3 solutions. X is 0. X is going to be 4/3 if you set, again, 3x minus 4 equals 0. and x is minus 3/2. So those are our three solutions. And this would be a nice one to check on your calculator because your zero feature will give you those fractions, or at least visible equivalents of them. For number 3, determine the relative maximum and minima of this thing in a classic calculator problem. So let's type in x to the 5th plus 3x squared minus 8x minus 4. And they give us a specific window. Minus 4 is the x min, 3 is the x max, and then the same zoom 6 features on that. So here's our graph. We can see a relative maximum there. It's a local maximum or relative maximum, but not an absolute. There's higher points. A relative minimum, not the lowest, not the absolute minimum. There's lower points. So let's go ahead and find these. I'll find the maximum first. And let's see, a left bound, 1, 2, say -2 is a left bound, and 0 is a right bound for that maximum. And skip that, and it says the maximum is at x equals minus 1.338, and it is y equals approximately, these are approximations, 7.786. The minimum, I can use 0 as a left bound, and I can use 2 as a right bound for the minimum. And I see the minimum is at x is approximately 0.866, and it is y is approximately minus 8.191. Now, as to when it's decreasing, we can see it's decreasing from this x value to the x value here, or on the interval however you want to write it. The interval is probably preferable. And if I was to try to, give some work to show what I did, I graphed this as my y1, and that's my window, and I would just draw this picture. Just sketch it, just a very rough sketch. Something like this. That's the 1 minus 1.338, and that's the 0.866, etc. Okay? All right. Write the equation to the line in slope-intercept form, which goes through these points. Well, first thing is I would find the slope here. The slope would be, again, difference in y values, 3 minus -5 over minus 3 minus 3, which is an 8 over a -6, or a minus 4/3. And the point slope formula gives us that I'll use, I guess it doesn't really matter, I'll use this point in my slope. Y minus y1 is m times x minus x1. For the point slope formula, think of it as a function which takes in a point, and the slope goes into this formula, and what comes out is the equation of the line. So this is the equation of the line. All we need to do is clean it up, and I'll do that on a separate piece of paper real quickly. We have y plus 5 equals -4/3 x plus 4. Y equals -4/3 x minus 1 would be the final answer here. And you can check that it goes through 3, -5, and it goes through -3, 3. The second one, we want a line that's perpendicular to this. There's the M here. And that tells us that the perpendicular slope is going to be positive 2 over 3, opposite in sign, reciprocal in size. And we can go straight to the point slope formula again. Let me put this here. So we have y minus y1 is m times x minus x1. So y minus 1 is 2/3 x minus 4. So y is 2/3 x minus 3. And again, you could draw pictures of this and check that it goes through 6, 1. Okay, this next one we want to solve this and then round our answer to 4 decimal places. Let's go ahead and solve this algebraically. First thing is we want to solve for this little exponential chunk. Then I would ABC it. X plus 2 is the log base e, also known as natural log. And finally, x is natural log of 8 minus 2. And we can approximate that fairly easily. Natural log of 8 minus 2. And we want 4 decimal places, 0.0794. Then a free response. Find all the real zeros of this function. Well, a couple ways of doing this. Calculator. But that probably wouldn't be very worth much in this free response section. We're going to do it with w squared minus 3w minus 4 equals 0. I'm just going to go ahead and factor it because it does factor. If we require the quadratic formula, the w substitution might be useful. I'm going to go ahead and factor this as x squared minus 4 times x squared plus 1 equals 0. Remember, the zeros are when f of x equals 0, or when the graph crosses the x-axis. And you can check that this multiplies out to x to the 4th minus 3x squared, the o and the I terms, minus 4. So this gives me x minus 2x plus 2. Now all the zeros are x is 2 and negative 2. The solutions that come out of this are plus or minus I, but they're not real, so we're just going to stick with plus and minus 2. Now this next one, this one has to be done on a calculator. There is a formula that will solve cubics. We just don't have access to it at the moment. So to do this one on the calculator, we would go ahead and type in. There's a couple ways. I'm going to go ahead and type it in as 0. I'm going to type in x cubed minus 2.6 x squared minus 3.93. Zoom 6. And I see exactly one real 0. And if you study a little bit more, if you take pre-calculus, you can be assured that that's the only real 0. There are no more. And to define that 0, we can use the second trace, number 2. Left bound, sure. Right bound, if I counted them, let's see, 1, 2, 3, 4. I'll just put 5. That's a good right bound. And so the 0 is at 3.028. Say 5. No places, no places. X is approximately 3.0285. Okay, and again, the work I would show would be something like this. And say I used second trace. Zero. Solve graphically. Interestingly enough, this one can't be solved algebraically without some work, whereas this one can be solved algebraically fairly easily. You might check that w squared plus w minus 2 equals 0 captures the form of this, but we just want to solve this graphically. So, and again, instructions. All right, so we're going to type in x raised to the 2/3 plus x raised to the 1/3 minus 2, and zoom 6. Okay, it looks like there was a solution out there, a little way out there. Not really clear. It's definitely a solution in there. Okay. As far as that, I'm going to go ahead and take a shot at that solution if it's between minus 10 and 10. Remember, if the solutions don't appear in this Zoom 6 window, well, that's why using a calculator is not always the greatest thing. It's going to be a lot easier to solve this algebraically and be sure that you have a complete and correct list of solutions, whereas solving the calculator, we have approximate and possibly incomplete list of solutions. So let's go ahead and take a shot at it. Well, we can certainly find this one. Second trace, 0. And left bound would be 0, yes, and a right bound might be, say, 3. And one solution is at 1, 0, and it looks straightforward enough. X equals 1. And another solution, I think there's one out there. And I'm going to make the left bound negative 10, and the right bound, say, negative 5. Let's see if we get a hit off of this. Tick-tock, tick-tock, tick-tock. Oh, negative 8. That's a nice one. Nice exact solutions. Negative 8. Oh, look. The cookie fairy. Yum, yum. Let's take a cookie break. Thank you, sweetie pie. Okay. Okay. Back to algebra. Again, if I was to try to annotate this, I would say we have a graph that looks something like that. It's got a solution at negative 8 and positive 1. Not the prettiest picture, but it's decent. And again, solving algebraically, if you notice that this is x to the 1/3 squared plus x to the 1/3 minus 2 equals 0. W squared plus W minus 2 equals 0, where W is the cube root of x. W plus 2, W minus 1 is 0. So W is negative 2 or positive 1. So that says that the cube root of x is negative 2 or positive 1, which says that x is negative 2 cubed or 1 cubed, which is, of course, our negative 8 and our positive 1. So it was a lot easier to solve this one algebraically than graphically, at least in my mind, whereas this one is pretty difficult for us to work, or impossible for us to work technically, because we don't have access to the cubic formula. Okay. Next one is a question involving this cost function. It's a quadratic cost function. It tells us the total daily cost by producing so many sodas. If we put in N is the number of sodas we want to make, then the output will be the cost of making those sodas. And presumably this is in dollars, and N is just numbers of sodas. To maintain a minimum cost, what is the number of sodas produced each day? Well, I don't like this wording. I'm going to say obtain. And what should we produce each day to minimize cost? Well, if you look at this cost function, and you can look at it different ways, but it is a parabola, and it opens up. And the minimum will be at the vertex. So we could graph this. It's just that probably the scale is a little horrendous with that 80,000 there. So C is a parabola. It opens up, which means it has a minimum cost, and the min is at the vertex, which is at, in our case, N is minus B over 2A. And remember, these are not in standard form. In any case, B is negative 120, and A is 0.055. So let's see. We have negative 120. Well, actually 120 divided by 2 times 0.055. Around 1,091. They should produce about 1,091 sodas to minimize their cost. What is that minimum cost? Well, in our case, let me see if I can think of a way to do this. I'll go ahead and put in that whole number. It only makes sense to put in whole numbers. And let's see what we get then. So we get 80,000 minus 120 times 1091 plus 0.055 times 1091 squared. And to the nearest penny, it would be $145,344.26. And here they're emphasizing algebraically solve this. Okay, well, leave your answer in simplest radical complex form. So, hint, hint, quadratic formula. Standard form. Again, we need standard form with this. X squared minus 7x plus 13 equals 0. X is the opposite of b, plus or minus the square root of some stuff all over. 2 times a is 1. B squared, 49 minus 4 times a times c. 4 times 13 is 52. So we get 7 plus or minus the square root of negative 3 all over 2. So we get 7 plus or minus I squared root of 3 over 2. And to be absolutely correct, 7 halves plus or minus square root of 3 over 2 times I. That's the A plus BI form. And let's see, number 11, we have a projectile that's been launched with a certain velocity, and it starts off at 40 feet. How long until it reaches maximum height? I'm going to go ahead and see if I can put this one in my calculator and get some interesting. And don't forget, you could check those answers on your calculator, because your calculator does do complex arithmetic. That is, you can plug the numbers 7 plus I squared root of 3 over 2 in. So if you wanted to, for example, there's a way to do that. Yeah, I guess I could take 7 plus I is right above your decimal point. And if I stored that in a letter, say call it A, and then I wanted to check that A squared minus 7A plus 13 was 0. Then I got at least one check on my solution. I didn't check both roots, just one of them. Let's see, minus 16, I was going to graph this one. Let's go ahead and see if we can get a graph of this one. So minus 16x squared plus 98x plus 40. And I'll make my window. Let's see. Time is only going to go positive. We'll go 10 seconds. And we'll make, let's just hit zoom 0. Zoom 0. Zoom fit. So for the first 10 seconds, we see it starts at height of 40 feet, goes up, 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 reaches its maximum, then it goes down. It hits the ground and the model ends, because we can't have negative heights with respect to ground level. So the model is only useful up to the point it hits the ground. After how many seconds will the projectile reach its maximum height? Well, second trace maximum. Left bound, I'm going to say, is 2. Right bound is 2, 3, 4, 5, let's call it. And it reaches its at 3.06 seconds. This is, and by the way, this is t equals minus b over 2a, which is, that's the exact value, which is minus 98 over 2 times minus 16. And we can check that minus 98 divided by parentheses 2 times negative 16, 3.0625. Okay, that's the exact value of the vertex. What is the maximum height? Oh shoot, I left that off. So second trace max, left bound 2, right bound 5, guess, enter. 190, we'll go with 190 feet to the nearest foot. It doesn't ask us. So this is in feet. And again, you can check. That number should be S of 3.0625. That's minus B over 2A there. So if you were to evaluate the function, you should get very close to 190 feet. And I'm rounding off here because it makes sense. Solve the following equation by completing the square. Here's one of those ones where we can do it. Allow you to complete the square or solve by the quadratic formula. So we'll do both. So completing the square, to be absolutely honest, standard form, x squared minus 6x plus 34 equals 0. Now I'm going to go this way. Quadratic formula. And then I'll complete the square. Well, I'll do it in the other order. X squared minus 6x plus blank equals negative 34 plus blank. Half of this number is negative 3 squared is 9. You need to add 9 to both sides. And again, this depends upon the leading coefficient being positive 1, sorry. That is a perfect square by design. Negative 34 plus 9 is a negative 25. No, that's 34 minus 9. My brain is seizing with chocolate cookies. It was negative 25. Peanut butter and chocolate cookies. Plus or minus square root, which you might recall is plus or minus 5i. So x minus 3 is this, and so x equals 3 plus or minus 5i via completing the square. Good to go. Quadratic formula. X is the opposite of b, plus or minus the square root of some stuff, all over 2 times a, which is 2 times 1 again. B squared minus 4ac is fairly large. So we have 6 squared minus 4 times negative, just plain old 34. We get negative 100. So the discriminant is negative 100. And so we get 6 plus or minus 10i over 2. Remember how we calculated these? That's the square root of 100 times the square root of negative 1, and that's 10 times I. Remember, I is the square root of negative 1. And we get 3 plus or minus 5i again. Same answer both times. Finding the inverse of the function. Pretty standard. F of x is x cubed minus 2. Check that it does pass the horizontal line test, but here's the same function. Here is its reflection across the line, y equals x. So x equals y cubed minus 2 is its reflection. And to solve this for y is to write it, I'm going to divide. We're going to take x plus 2 and then take its cube root. And so we get then that f inverse of x is the cube root of x plus 2. And you can verify this a number of different ways. You could compose f and f inverse in both directions and show that it equaled x, that f, you could, if you wanted to, check. You don't need to. If you wanted to check, you could check, for example, that f of f inverse of x was x. That is, that f of the cube root of x plus 2 was equal to x. And you could see, let's see if this works out. F of x was x cubed minus 2. So we take the input, cube it minus 2, and the question is this equal to x? And we can see that this is x plus 2 minus 2, and that direction works. And you could do the other direction to show that it worked as well. Number 14 is a pretty standard exponential. I would ABC this. The exponential portion is all by itself. And I would write this as x plus 3 equals log base 2 of 11. And the solution then is x equals log base 2 of 11 minus 3, which can be approximated on your calculator fairly easily. Don't forget the change of base formula. So we're going to have, for example, I'm going to go ln. ln 11 divided by ln of 2. There's my log base 2 of 11 minus 3. 0.4594. 0.4594. The next one down here is a fairly standard logarithmic equation. You can expect some of these. And for this one, it's up there. We have the log base 3 of x plus the log base 3 of x minus 2 is 1. To solve this, and again, your calculator would probably solve this reasonably well. We might check that. Combine the two logarithms into a single one, and now just like this, you have a single exponential expression, a single logarithmic expression, and you can ABC it. That is, simply convert. And we get x times x minus 2 equals 3 to the first power. X squared minus 2x equals 3. X squared minus 2x minus 3 is 0. X minus 3 times x plus 1 equals 0. And by the principle of zero product, we get x is 3 or negative 1. And don't forget, you need to check. We can check that both of these don't work. Only 3 works. And that is literally take it and plug it in, and you'll find, in this case, you'll find you can't even plug negative 1 in. So remember, a solution has to fit in the equation to make sense, and then it has to read true. Here we have some graphing problems. Graph by hand, fill in 5 points in the t-table, etc., etc., etc. And again, it's horrible graph paper where I can barely see the axes. Go ahead and draw these axes. You should get better graph paper on your exam than what we're seeing here. Okay. So let's see. 1/3 to the x. One thing I know about this is that it's an exponentially decreasing function. So I know it looks something like this. That's the shape of it. And that goes through 0, 1. And you could actually plot a bunch of points. You could just pick, negative 1, 0, 1, 2, 3. Is that 5? Yeah, that's 5. 3, 1, 1/3, 1/9, 1/27. It's pretty easy to put them in. Over here, if you wanted to, this one's exponentially increasing. Something like that. And I could pick negative 1, 0, 1, 2, 3. And if actually this one has been shifted up by 1 unit. I've got that plus 1. 2 to the x, here's what 2 to the x looks like. That's 2 to the x. It goes through 0, 1. So if we shift everything up by 1 unit, we get something like this, 2 to the x plus 1. It's been shifted up, so lift the whole thing up. And we'll graph this. So that's going to be a half, plus 1 is a half. That's 2. That's 3. That's 4 plus 1 is 5, and 8 plus 1 is 9. So if we're going to plot this, let's make these, like these will be my 1s here. At 0, it's equal to 2. At 2, it's equal to, at 1, it's equal to 3. At 2, it's equal to 5. 1, 2, 3, 4, 5. That's at the end of my graph. So at negative 1, it's equal to 1.5. Those 3 halves. It's not, yeah, that's 3 halves right there. Check that on the calculator. This would be a good idea. And at -2, if we wanted one more point, it should be at 1.25, which is, I think, 1.25 right there. Okay. There's a picture of it right there. Okay, it has a horizontal asymptote here. Okay. And again, if we were to look at these on our calculator, 2 to the x plus 1. 2 raised to the x plus 1. See that horizontal asymptote? It's so close to the horizontal asymptote. Normally when we look at 2 to the x, we don't see the tail end of the graph getting closer and closer. If we were to draw the horizontal line at level 1, so they almost hit each other. Let me go ahead and make this into something else. I make this one heavy, make this one light. There's our graph. And there's its horizontal asymptote. I don't know if that looks any better. Okay, log base 2 of x. Now you can do this lots of different ways. If you wanted to think about y equals log base 2 of x, you could certainly write this as 2 to the y equals x. And then you could pick a bunch of y values, right? -1, 0, 1, 2, 3. And your x values would be 2 to the -1 would be 1/2. 2 to the 0 would be 1. 2 to the 1 would be 2. 2 to the 2 would be 4. 2 to the 3 would be 8. Something like that. And you could plot these points. You could also recognize that this is a basic logarithm graph where the base is larger than 1. Looks like that. And let's go ahead and do this on the calculator also, just to kind of fill the bill. Log base 2 of x would be, say, for example, log of x divided by log of 2. Zoom 6. Looks something like that. And don't forget, this is an asymptote right there. So what's actually happening in trace mode, let me zoom. Hey. Here. Oh well, I guess we can see it there. You can see it coming down asymptotically towards this. And if you wanted to, you could use a table of values and you could just type in, you see I've got a bunch of values here, 1, 2, 3, 4, 5, you could just type numbers in and you get a t-table pretty easily. You should try to make sure that your graph shows points that are actually visible, namely your t-table or your table of points should actually fit on here. So whatever your scale is, if your scale is 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, depends on what your scale is. This next one, if you look at it, it's the previous one that's been shifted left by 2 units. So what was the y-axis is now this invisible, non-existent vertical line at -2. And what was at 1, 0 is now here. And so the graph would look something like this. Okay, and you could just take all these points and move the x-coordinates over. So, for example, subtract 2 from each of these. Or equivalently, you could go to your calculator and you could see insert +2. Oops, let me go zoom 6. Here's the original graph. And remember, the graph doesn't die here. It goes on forever in that direction. It's actually increasing. Its range is all real numbers, all y values. Its domain is everything that's strictly larger than -2. And if I was to draw, I can't draw a vertical line here, but as I move to the left, it will continue see the graph gets closer and closer to this line y equals -1.96. And then the problem is the pixels here move it. So this is more of a caricature sketch of it, but this would certainly suffice. And I would make my graph. There's my vertical asymptote. Here's my x-axis. Here's my y-axis. Okay, everything's been shifted to the left by 2 units, and so it's going to go like this. And you should try, within reason, to make your graph match the points you have here. But if you wanted to, in a table values, I could just write these down, and they're on my graph. At 0, it goes to 1, so it should go through 0, 1. There's 0, 1, so 0, 1. It goes through 1, 1.585. It goes through 2, 2. It goes through 3, whatever. 2.322. It goes through 4, 2.585. Blah, 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 and you're done. Number 18. Here we have a nonlinear inequality, and we can solve this a number of ways. Some hybrid way would probably be best. And first thing we're going to do to solve this is put it in standard form. And from standard form, we're going to want to find out when is this guy equal to 0. Standard form means this is either less than, greater than, less than or equal to, greater than or equal to 0. And this one can be factored. They can't all be factored. We're lucky here. And you get x squared minus 4 times x plus 3, and these solutions pop out. And you get x is 2, -2, or -3. And now these solutions on a number line mark off as there's 2, there's -2, and there's -3. The scale is not really important here. I know it's a horrible scale. 0 is in between those. These points actually are going to be in my solution set, and we'll get more detailed in the future when we're doing sign charts, but I'll put up with dark circles because I happen to know or equal to. And these are the zeros. And now I need to take test values, and here's where my calculator can come in handy. I can graph that function, and it's x cubed plus 3x squared minus 4x minus 12, and zoom 6. I don't know where my scale has been. You can see the graph of the function is negative to the left of -3, below the axis. It is positive between -3 and -2. Then it's negative for a long period between -2 and 2, and then it's positive after that. And again, if you wanted to find those points, you could do this the same way we did before. So for example, if I wanted to find that is the first 0, and you can find these zeros, okay? But for us, we have a sign chart now, and again, this is below the axis, above the axis, etc. That's what they mean, below and above the axis, minuses and pluses. And we wanted the less than, the below the axis, or touching. This is below or touching the x-axis. That's the minuses, and this is the zeros. So I can simply get this. I can color in the parts I want to keep. That and that represent my solution, or equivalently, minus infinity to -3 bracket union -2, 2. Or equivalently, x less than or equal to -3, or you can write union, -2 less than or equal to x less than 2. All three of these answers are equivalent and correct. The next one's a similar one. We have x cubed is greater than 4x squared minus 3x. And standard form, x cubed minus 4x squared plus 3x is greater than 0. And we factor out a GCF. And we have x minus 3 and x minus 1. Again, we're trying to make a sign chart for this expression. In the end, we want above the axis only. That is the pluses. And we can see the places where it crosses the axis, so the zeros are 0, 3, and 1. So on a number line, mark off 0 and 1 and 3. Now I happen to know we're not going to want them, so I'm going to go ahead and leave them as open circles. I just marked them. And again, you could do this more or less on this, and there are ways. I'll go ahead and type this function in. It's x cubed minus 4x squared plus 3x, zoom, 6, standard window. And we're seeing, okay, I see below the axis, a little bit above, below, above. So it is above the axis to the right of 3. And again, there's 3, there's 1, and there's 0. And it's below the axis, then it's above the axis, then it's below the axis. And you can check these. Normally we check these with what are called test values. Occasionally the graph is too small or too large to simply look at the points. For example, if this had been 0.001, it'd been very hard to visualize a little piece that lies above the axis. This is even kind of small. There's a little portion that's above the axis. So we have the sign chart, and we could use a table of values. That's how we normally do it. We would pick numbers to the left of 0, like -1. Pick a number between 0 and 1, like 0.5. Pick a number between 1 and 3, like 2. And pick a number to the right of 3, like 4. And you can see we get minus, we get a positive value, we get a negative value, and we get a positive value. And all that matters is the sign of what comes out. For various reasons, the sign of the number in here will always be the same. It will always be positive to the right of 3, regardless of which number we choose. So we might as well just choose any number, like 4 or 5 or 6, and we'll always get a positive number. Okay? So in our case, we want the greater than zeros, which is the pluses, and so I'll color this in, and I'll color this in. And again, you could write this as 0, 1, union 3 to plus infinity. You could write this as x is less than 1 and at the same time greater than 0, or x is greater than 3. So any one of these three would be fine. Okay, and here we come up with a absolute value inequality, fairly standard. The transformation is 3x plus 2 is greater than 7, or 3x plus 2 is less than -7. Remember, with these absolute value equations and inequalities, as long as you're comparing it to a positive quantity, anything greater than or equal to 0, the transformation looks like absolute x equals a, greater than a, or absolute x is less than a, each of these. And I'm going to say, assuming a is greater than or equal to 0, we'll get x is plus or minus a, x is greater than a, or x is less than the opposite of a, x is less than a, and x is greater than the opposite of a, namely minus a is less than x is less than a. And again, pictorially, remember the absolute value of a number is its size. Right? If the absolute value of x is precisely equal to a, the distance it is from 0 is exactly a, it must land here or here. If the size of x, the distance to the origin, is more than a, it must be to the right of this, or equivalently to the left of this. And finally, if the absolute value of x is less than a, then its distance to the origin is less than a, it must be within a units of the origin. Okay? In our case, we have these two inequalities, and we can solve them individually. 3x is greater than 5, x is greater than 5/3, or 3x is less than -9, x is less than -3. So here's one form of our answer. And you could write this different ways. You could write this as a picture, -3 5/3, open circles to the right of 5/3, or to the left of -3. You could write this as bracket parentheses, minus infinity minus 3 union 5/3 to plus infinity. Any of those would be fine, unless some particular format was specified. 21, write the equation of the circle in standard form, which has endpoints of a diameter at -4, 1, and -2, 3. Okay, so here's where a nice mental picture can help. It's not necessary to have a beautiful picture, but a little picture can help. -4, 1, 1, 2, 3, 4, 1, right there, and 2, 3, 1, 2, 1, 2, 3. So this is supposed to be endpoints of a diameter, and we can visualize the circle. It looks something like this. right? And to come up with the equation of the circle, we need to know its center, and we need to know its radius. And we can see the center will be the midpoint, and the radius will be half the length or the distance. And so let's find the midpoint of this segment. So the midpoint, which is our center, remember, that's HK, will be the average of the x's, so negative 4 plus 2 over 2, and 1 plus 3 over 2, which is negative 2 over 2, which is a negative 1, and 4 over 2, which is 2. So negative 1 comma 2 looks pretty good. That's our center. That's our HK. And we can either take the distance from here to either of these points, or take the distance between these points and halve it. And I'm going to go ahead and just go straight for the radius. So I'm going to take the distance between negative 1, 2, and say 2, 3. Because that will be our radius directly. And so this r will equal the square root of difference in x's squared plus difference in y's squared, which would be negative 3 squared plus negative 1 squared, which is 9 plus 1 is 10, square root of 10. So r is the square root of 10. So we know that hk is this, and r is this. So the form, remember, is x minus h squared plus y minus k squared equals r squared. So for us, we have x minus negative 1 squared plus y minus 2 squared equals the square root of 10 squared. And you can clean that up. I mean, it's not really important. X plus 1 squared plus y minus 2 squared equals 10 would be the cleaned up version of the answer. Number 22, we have a company. It's the sales. The sales is 100 times the log base 2 of x plus 2. X is the number of weeks after the advertising campaign was introduced. And we want to know the total sales 6 weeks after the campaign was introduced. And that sounds like this should be S of 6. And I'm going to go ahead and type this in because we'll probably use this. 100 times the log base 2 of x plus 2. And we're going to use a change of base formula here. So I'll use ln just to be different. ln of x plus 2 divided by ln of 2. Okay? Don't forget the log base 2 of x plus 2 is the log new base of x plus 2, which would be e, divided by log new base of your old base. Okay? And I'm going to make a window. I don't know what window. Maybe make this 0 to... Let's make it 15. We'll do 15 weeks. And we'll see what we need. Wow. Hey, let me see my window again. What happened to 0 to 15 weeks? Zoom 0. Here's my 15 weeks. Here is a graph of increasing sales. And if we wanted to know what it was at 6 weeks, we would say 300. And this is in thousands of dollars. So I would say this is $300,000. That was the total sales 6 weeks after the ad campaign was introduced. The second question said, when will the weekly sales reach 400,000? So here's where I'm going to draw a horizontal line at level 400. And not surprisingly, my window just fit in the first 15 weeks. Remember, choosing the appropriate window can be key here. Second trace intersect. First curve, yes. Second curve, yes. There's only one intersection I'm interested in, and it is at 14. At x equals 14, and that would be 14 weeks after introduction of the ad campaign. Now we can do this algebraically. I mean, we can't evaluate the function algebraically. At least we can't come up. So to do this algebraically, let me see if I can find some paper here. Might as well. Useful. We want to know when 400 equals 100 log base 2 of x plus 2. That's what we need to solve. So divide both sides by 100. Rewrite things, a, b, c. Okay, and we get the same answer this way also. Okay, this next one we have a compound interest problem. And again, I'm going to use my calculator. I'm going to type this in. How do I know I'm going to use my calculator? Well, we're definitely rounding off our answers. So we have 10,000 times e to the 0.054x. Continuously compounded interest at 5.4%. And we want to know how much is the money is in the account. It's a single deposit. How much is in the account after 1 year, 5 year, 10 years. And I'm going to go to a table. 1, 5, 10. And we see the money in the account is $10,555. $10,555. After 5 years, it's $13,100, and after 10 years, it's $17,160. To find out when will the account have $15,000 in it, we can again do this algebraically. We could simply set 15,000 equal to 10,000 e to the 0.054 t, and we could solve that. Let's go ahead and do that. That might be easier than the graph, because the graph will have to worry about the scale. So let's see, divide both sides by our 10,000, and we get 1.5 equals e to the 0.054 t. Rewrite logarithmically. Log base e of 1.5 is 0.054 t. And so the natural log of 1.5 over 0.054 should be t. And that will be approximately, let's see what that is. So the natural log of 1.5 divided by 0.054, around 7.51 years, depending on how you want to do it. 7.5 years is probably reasonable too. Alternatively, you could do this by graphing. My window would be 15 years. I'm going to hit zoom fit, adjusting my X window, and here is my exponentially growing account. And after 1 year, we see we have $10,555. After 5 years, we have $13,100, pretty close. And after 15 years, 10 years, we should have $17,160. Okay, and again, you could go to the nearest penny. It doesn't give us actually a rounding level. To find out when it's equal to 15,000, we could draw a horizontal line at level 15,000 and find out when these two cross. And it's around 7.508, etc., 7.51 years. Find the doubling time. Oh, okay. Well, doubling time. We could do this two ways. Didn't see that there. The original amount in the account was $10,000, and so doubling time would take us to $20,000. So doubling time with a calculator would be the intersection of the original graph. Here's our account growing exponentially, and there is when it reaches double the original amount, $20,000. Second trace intersect. First curve, yes. Second curve, yes. Guess it'll find that point, and around 12.8 years. I'm going to go. And if I was doing this, for example, I would show, on a calculator. If I was going to show my work in a calculator, I would say it looks something like this, looks something like this, and that guy right there. Something like that would be sufficient. Algebraically, which is your work, you would do something like, okay, we have 20,000 is the result of putting 10,000 into this account, and divide both sides by 10,000. You can rewrite this, and then we get natural log of 2 divided by 0.054. So natural log of 2 divided by 0.054, and you get 12.8, 12.9, depending on how you want to do it. And finally, we're left with 24, in which we have this word problem involving sodas, soda sales. And it talks about the average number of sodas consumed per hour at a softball game is linearly dependent upon the temperature T. That means that S is a linear function of T, or equivalently that S and T graph together make a line. Remember the classic line is y equals mx plus b, where y is a linear function of x, or y depends linearly upon x. And so in our case, S is mt plus b. And we're identifying x, y, in our case, with ts. And we have 2 points. In one case, the temperature was 90 and the consumption, S, was 2. So we have 90, 2. In another case, the temperature was 94 and the consumption was 3.5. So we want to find the equation. The first question asks us, what is that line? What is the equation of it? Well, we're going to find the slope first. M is 3.5 minus 2 over 94 minus 90, which is 1.5 over 4. I'm just going to clean that up slightly. Let's see, multiply top and bottom by 2, and you get 3/8. Okay, so the slope is 3/8. And we can use point slope formula, and you can do it with y's and x's, or I'm going to do it with s's. So s minus s1 is m times t minus t1. I'm using the point 90, 2. And so we get s minus 2 equals 3/8 t minus, let's see, that's 270 over 8. That's a boring number. And so S is 3/8 t minus, and I'll go ahead and figure out what 270 divided by 8 is, plus 2. $35.75. We don't mix and match. 143 over 4. So I'll go ahead and write that in. There's our function. S of t, or S, equals 3/8 t minus 143 over 4. And you can check that this satisfies the criteria going through 90, 2 and 94, 3.5. If the temperature reaches 98, what will the average consumption of sodas be? In this case, we want to know what S of 98 equals. And so we can do this on our calculator. We can say 3 divided by 8 times 98 minus 143 divided by 4. We get 1. And I believe that's sodas per hour. 1 soda per person per hour. Get the correct units on this. Okay. And the last one here is this hinky little function. And we have various questions. Where is it increasing? And remember, this is a closed circle here, so this graph has limited domain. Where is it increasing? Well, it's increasing, and assuming, I don't know what these points are, but I'm going to assume that each of these squares counts for 1 unit, and you should have a graph with a scale on it. So let's see, boy, this is a lot. It's increasing from -3, okay, -3. It starts increasing, and then it finishes increasing at 3. But then it's increasing out here some, 4, 5, 6, 7, 8, 9, 10, 11. That looks to be 11, 12, 13. And I'm using interval notation down there. Where is the graph constant? And if I was to look in here, I'd say 4, 5, from 5, 6, 7, 8 to 8. Constant. What are the relative maxima? This is a maximum, and that's at 1, 2, 3, 4, 5, 6, 7. In this case, 7 occurs when x is 3. And technically, 1, 2, 3 is a maximum. That's a high point, and it's at x equals 13. So that little black dot there is higher than nearby points. And remember, the maximums are the y values, and they are at their x value. The relative minima, there's one here, and that's at -3. -3. And that's at x equals -3 also. And any other local low points? Yes, -1. And that's at x equals 11. And let's see what else we have. What is the domain? The domain looks to be from here all the way to the left. So it looks like 12, 13 from minus infinity up to 13, close bracket, because that's a dark circle there. I have to go down. What is a range? Now range, we're going to assume that this keeps going up here, okay, and continues to cover the y-axis. It's not clear that it does that, but we'll assume it does because of the direction of the arrow. In which case, the y-axis will be covered from here to positive infinity. So 1 to -3, and I'm going to make that closed up to plus infinity. I'm going to assume that that point actually reaches -3. So I'm going to say that the range is -3 up to positive infinity. What are all the real zeros of the function? Real zeros are where it touches the x-axis, real numbers. So we have -4, -5. And -1 is a real zero. And any other? Yes, 8, 9, 10, and 12 are zeros of the function. Okay, so the real zeros are -5, -1, 10, and 12. And then finally it asks us, what's f of 0? F of 0, when x is 0, the y value is 2. That's because 0, 2 is on the graph. And f of -2 would be the y value associated with this, and I'm going to go with a -2 for that. So, and again, there's a bit of estimation on what the actual coordinates of the point are, but that's good. Okay, let's see. Oh, now we're into answers. All right, well, good luck on the exam, and I'll see you then.